Okay, so I just, like, as you guys know, I just had like 15 minutes to revise this thing. So, but I think I got the basic idea. So, and I looked at the code, and I kind of remember. So it's actually really simple. So, segment trees, right? To be honest, like if it's far easier than to reason about than even a trie or a union find data structure. Like it's but we can actually see that, right? So so the very first thing, right? So I think this range sum query mutable from LC, right? Like the problem 307. This is one of the most the basic use cases of a segment tree, right? So the idea is you're given a set of numbers, right? And then you want to do a couple of things, right? Like, so one is you want to query some function, right? So in range sum query, it's like the function that we want to query is the summation, right? The sum of between two indexes, right? Like, so index 1 and index 2, right? So that's the main goal. And and if that is all the question is, right? If I give an array and then, I say, what is the most efficient way? Lots of queries are going to come where give me the sum between, some index I and index j, then and that's all we have to support, right? So then, as you guys know, the simplest way to do it is using prefix sums, right? So that sounds clear, right? Like, so because there is no, let's say there is no update for now, so then you can simply build a prefix sum table, and then, like, you can always like find what is the sum up to I, you can find what is the sum up to j. If you reduce it, you'll get the sum between I and j, right? So then you guys, then you're basically done. So the problem actually arises mainly because like, what if I want to update, let's say, I think in this case I just want to update one index, right? So I think that is what this question also talks about, right? The update basically takes I comma val, right? So which is basically saying that I just want to update this particular value or this particular index to this new value, right? Now, if I want to support this and I still want to maintain a big of one query time performance, right? So then what I have to do is updating on the array is okay, but now that I'm also maintaining this prefix table, I have to like literally update every other index after this particular index I. Isn't that the case? I think, Madan, that's what you did, right? Like, so when you implemented it, you basically in the update
update is
function,
OAuth operation.
exactly, right? So in the update, you will basically go and update your prefix sum table.
Correct.
Right? Like, so
change
everything.
the num and then do the prefix sum.
And in the prefix sum, you'll start with whatever this current index is, and you'll basically make sure that you add that value to, or you add the diff to all the values from
take the diff for previous one and then
this one, and then you make it for every other index after this index.
After this index, if it is zeros index, it's all often.
Often, right? Yeah. So the worst case is often, right? So the question is, can we build this intelligently to and the data structure to do this is perfectly a segment tree. And one thing to notice, it's not just for sum, right? So here we are taking sum as an example. It's for a lot of these functions. Like if you want to find instead of sum, I can simply saying range min query, right? Or I can change this particular problem to range max query, right? And you'll exactly do something similar. You'll construct a segment tree, and there's a very small portion in the segment tree code that will actually change, right? So given that, let's actually look at what a segment tree is and how we build it, right? So this is from my notes from last year, right? When I gave the session to folks. So in this particular thing, let me enlarge it, right? Okay, cool. Right. So here, the array that we are actually taking in, right? So it's the first line that you're seeing here. The array consists of 1, 2, 3, 4, 5, 6, 7, 8. Right. So that's my array, right? So the concept of segment tree is very simple, right? Like, so you want to basically you want to store some aggregate value over a set of indexes, like by building a tree, right? Like, so I think that's one way of putting what a segment tree does, right? So in this case, let's say if you're base array is 1, 2, 3, 4, 5, 6, 7, 8, right? Like, and that's the contents of your array, right? The simple way to construct a segment tree is I'll actually using 1 and 2, right? I combine the 1 and 2 value, and because here we are talking about constructing a segment tree for to finding the sum, right? So what is the node that I'll actually combine is actually 3, right? Because it's 1 plus 2. So similarly, 3, 4 I take, and then the combined value is 7, right? And then 5, 6 I take, I combined value is 11, 7, 8 I take, the combined value is 15, right? So I form the next level by basically being able to combine from the leaf level, right? The leaf actually contains the real elements of the array, and then I form the next level by simply combining 2 elements and then forming a node, right? So now I have this combined information 3, 7, 11, 15, and then what I do is like I just do the process until I reach the root, which is actually one single element that represents the entire array, right? So in this case, 3, 7 becomes 10, 11, 15 becomes 26, and 10 and 26 finally gets combined and I form a single root element, which is 36, right? So this is the actual, so given an array, all we have to do is, like make sure that you basically construct a tree, right? And every level in the tree stores the aggregate sum of its leaf, right? So, and if you guys look at it, it's actually true, because what does this 36 at the root level mean? The 36 at the root level means it actually covers the entire index, right? So in this case, the numbers are 1 to 8, right? Which means the index of the original array that is given to me is 0 to 7, right? So the 36, which is at the root level, right? So that covers the sum, because we are considering a segment tree for the sum. So that 36 actually covers the entire range for the complete array. So 0, 7 is what this 36 covers, right? And then if you guys actually look at it, right, what is the range that so the left node for that is actually, so this is, if you guys look at it, right, we are almost kind of constructing a complete tree, right? So in which case, if your root is at index 0, right, so you don't even have to build a tree in a segment tree, right? This is like a heap kind of a thing. Like you can actually simply have an array, which means for 0, your left is 2 star I plus 1, your right is 2 star I plus 2, right? So, and if you guys look at it, if my root covers 0, 7, right, then what does my left tree cover? Right, because your left tree covers half, and then your root, and then your right tree covers the next half. Your root totally covers both whatever your left and right tree covers, right? So if your root covers 0, 7, and let's say you want to figure out what your left tree covers, right? You simply find the midpoint of the root, right? 0, 7, you take the midpoint, probably is 3, right? So your left tree is actually 0, 3, right? And then your right would be 4, 7. Right, and then if you actually look at the value there, the 0, the 10 that is there actually represents the combined sum of indexes 0 to 3, and your right tree represents the combined sum of indexes 4 to 7. And similarly, you can, like, so we saw how to combine the values from the leaf and go to the root, right? Now we are simply like decoding the process from the root to the leaf, right? So the root is at index 0 in the array, right? Like, so because the entire segment tree is stored as an array because it's a complete tree. And then the value of the root is 36, right? Which means we know that it covers the entire array. So the entire array is from 0 to 7. Right. So now what does my left child cover? My left child actually covers one half of the array, right? And that is basically from 0 to mid, right? A mid here is index 7 plus 0 by 2, which is actually 3. So 0 to 3 is covered by my left index, and then mid plus 1 to the end, which is actually 4, 7 is covered by my right index. So similarly, you can simply do the same thing, right? Like you take 0, 3, you find the mid, right? Which is actually 1, right? So which means that 0, 1, that's the index that's covered by that particular node on the left. And then everything from mid plus 1 to whatever this range ends, right? Which is mid plus 1 here is 2, and the range ends at 3, right? Because you're basically splitting 0, 3, and mid is actually 1. So 0 to 1 covers the left, and 2 to 3 covers the right, right? And finally, if you guys look at it, the leaf level, right? Because they are actually individual elements, right? They don't represent a range. They are just individual elements. But if you guys actually think about it, the range is just nothing but the start and the end are the same for the leaf, right? Like it's each one is basically 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, and 7, 7. Does this actually sound intuitive to you guys, or do you guys have any questions on this? Because once this is clear, going through the algorithm is like next 5 minutes, and then we are done with segment trees.
If the range sum is between 1 and 3, then that's where we have to do some. some other way to, right?
Oh yeah,
Because
yeah. So right now, we don't even, we have not even started talking about how to query or how to update.
okay,
Right, like
got it.
so
Yeah,
right now all we
structure.
are, yeah, exactly, all we are like using this whatever we said as of now, right? If we go and look at the code for how to construct a segment tree, we should be very clear, because if this logic is clear, then the code to construct the segment tree is like very simple recursive process.
Mhm.
Right, like so so you guys are completely fine with whatever we have here, right? Like, do you guys have any questions with respect to, so every node, if you guys look at it, right, all these numbers are actually pretty important, right? Every node, like you see that 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14, so those are your actual because we are storing this, if you guys remember, a complete tree you can always store in an array, right? You don't actually have to construct an explicit tree for that, right? So right now we are going to assume a complete tree, and we are going to assume that like all my input array sizes are in the power of 2, right? And basically we'll see basically how to deal with when we get an array that doesn't have a power of 2, right? So but for very simplistic sake, we can assume that it's made up of a power of 2, and then like, which means you can perfectly, starting from the leaves, you can perfectly construct this whole tree, and then you'll basically get the root. And what does the 0 1 2 3 4 5 6 7 to 14 represent? That simply represents like your 0 is for actually your root level, right? Like, so the root is numbered 0, which means that your left is 2 into I plus 1, which is basically 2 into 0 plus 1, which is 1, and your right is 2 into I plus 2, which is 0 into 2 plus 2, which is actually 2, right? So, and then you can simply calculate what your index number for your left and right based on that formula, 2 into I plus 1 and 2 into I plus 2, right? So that is what this 0 to 14 mean. And what does all this bracket numbers mean, right? It literally means what is the range that I cover at this particular thing, right? So root covers range from 0, 7, right? Because it's a complete tree, you have exactly in this case, you have exactly 2 power 3 leaves, right? Which means your index that covers 2 power 3 is 0, 2 power 3 minus 1, right? So it's 0, 7. So your root covers all the values. So which means your starting index for whatever root covers is 0, and the ending index, whatever the root covers, is 7, right? That represents your entire leaf array, right? Like the all the nodes from 0 to 7, your root covers, right? And similarly, if you simply apply the formula, right? Like, so find the mid, and then like up to the from whatever this comma start, and the mid is covered by a left, mid plus 1 to end is covered by a right, right? So in that case, you can always figure out like what is the range of your left value, or what is the range of your right node, right? So, and then similarly for that particular node, right? Like, so you can always find the mid, figure out what the range of the left is, figure out what the range of the right node is, right? And so that is the significance of this. Like, so every node has its own index value, right? Like, which is actually the 0 to 14. Every node also represents a range, all right? It represents a range, and every node also has a value, right? That value is what we see 36, 10, 26, right? And that's nothing but, and in the sum, how do I build that value? Each node's value is nothing but, if I build the left subtree and right subtree, then the value for me, which is the parent, is nothing but the sum of my left subtree and the sum of the right subtree, right? And you guys see that this 36 is nothing but the summation from 1 to 8. So before we go and look at the code for this, right? So, which is exactly what I described as of now. We are not going to do anything extra. Are you guys clear with this tree structure?
Yes.
Okay, cool. So let's go to the code and see is what we just discussed is what is being happening over here, right? Okay, so yeah, so this init, right? So the init is the function basically where I'm kind of creating this whole process of creating the tree happens over here. And in the init, you're actually passing nums, right? So this nums, for in our example, this nums is nothing but the array from this particular thing, right? That nums is the array that contains 1 to 8, right? Like, so, and as I said, for now, let's assume assume a complete tree, which means like your size of the array is 2 power some x, right? So in this case, it's 8. And then now that you guys have that nums over here, right? The question is like, how do I do this recursive construction, right? So we basically, then we actually start from this, right? So this is where we actually do this, right? So I have my own self.array, right? So whatever this ARR, where I actually store the nums, right? And then the self.end is nothing. So this n here is the actual length of the given array, right? So we have two arrays totally. If you guys look at it, we are going to have two arrays, right? One is whatever is given to me, and the other one is whatever segment tree that I'm going to construct, which I'm actually going to store it in an array form, right? So the ARR is the input array, and then I actually create, if you guys see this line, self.tree equal to 0 into self.get tree size of len of nums. So all here I'm doing, right? I'm creating enough array elements to actually hold this entire tree made up of 0 to 14 elements. Right? And how am I getting this? How am I getting what the size of this thing, right? The size of this thing, the way I'm getting it is, if your leaf is consists of 2 power n elements, right? Then if you guys remember, in a complete tree, if the leaf is made up of 2 power n elements, then the rest of the size of the rest of the elements, right? The basically all the upper levels is actually equal to 2 power n minus 1. You guys remember that, right?
Sorry, say that one more time, Raj.
So
sorry,
if,
Raj.
If your leaf is in a complete binary tree, right? So in a complete binary tree, if your leaf consists of 2 power n elements, in this case, your leaf consists of 2 power 3 elements, right? So what is the size of the complete binary tree?
I don't know. Sorry.
Right. So no problem. So it's basically because it's a complete binary tree, right? It's actually nothing but your first your level 0 will contain 2 power 0 elements, which is actually
Correct.
1. The next one will contain into 2, right? So because you're just exactly like dividing it into 2 at the next level, right? So and then the next one will contain, so which means you start with 2 power 0, then it's 2 power 1, and then it's 2 power 2, and then it's actually 2 power 3.
Okay, that's essentially saying 2 power n minus 1. Okay.
Yeah, so the 2 power n minus, the 2 power n minus is going to come because if you have 2 power 3 elements at the leaf, so it's just a property of the complete binary tree, right? If the number of elements of the leaf is 2 power, if it's 2 power 3, then the rest of the subtree, right? The entire rest of the subtree without including the leaf is exactly the double minus 1. So in this case, you have 8 elements in the leaf, right?
Correct.
So the rest of the elements would be so not exactly double, exactly the same. So in all your other levels, if you count it, the number of nodes will exactly equal to the total number of nodes in the leaf, but you have to subtract minus 1 from that. So here you have 8 elements in the leaf, and now you forget the leaf, and look at how many elements are there in the rest of the subtree. You'll actually have 7, right?
Yeah.
So that's so it's just a property of the complete tree, right? Like, so in a complete tree, the total number of elements, I mean, another like logical way to think about it is like, how many number of elements do you have in a complete tree? If the number of levels is, let's say, in this case, the number of levels is 1, 2, 3, 4, right? So the number of levels is 4. Then in a complete in a complete tree, you will actually have 2 power n minus 1, I guess, right?
Yeah, same. Yeah, right. What I was saying is correct. Exactly right.
Yeah. Right? So it's 2 power n minus 1. So we have exactly 0 to 14 indexes, which means it has 15 elements. Right? So you guys get this, right? It's just all this has nothing to do with actual segment tree, right? It's given that, you have a complete tree. What is the property of complete tree? How many nodes? Because here, the reason why we are looking at this specific property of complete tree is because here we are given the leaf, right? Like the current array that we are given is nothing but the leaf level, right? So in order to actually create the total size for the complete tree, I have to figure out what the array size is, right? So that is why, like we simply look at this one property where if your leaf is made up of 2 power n elements, then your total array size is nothing but the 2 power n, which is for the leaf, plus 2 power n minus 1, which is for all the other elements. So in this case, it will be like 8 plus 7. Right? And that is all I'm doing over here. If you guys look at this code, right, I'm saying, hey, get me the tree size, right? So in this tree size, so you guys can forget the first line. The first line is actually handling the case where the input array is actually not a size of, it's not a power of 2. Right, so you guys can simply forget the first line for now, because it's a small adjustment that we make to make. I mean, basically the adjustment that I make is, if I'm given an array that is not a power of 2, I actually kind of consider that I actually have an array that is really a power of 2, right? So, and then I proceed from there because it's very easy to do it that way. I think there's exist solutions that do not have to create this extra size and stuff, but they are a little bit harder to reason about. This is like a very straightforward and like a very simple solution, which, and I don't think in an interview they're going to penalize just because we are going to create those, we're kind of converting the input array into a size of 2. Right, into size of power of 2, right? So so ultimately all I'm doing is it's 2 into the 2 power x minus 1, right? So that's the tree size I want. I need the tree size because, given the leaf, all I'm doing is, like in this particular all I'm doing is, given this leaf array, I want to figure out what is the total number of elements that will be there in the tree. And we saw that, assuming that the leaf is power of 2, I would it's nothing but that 2 power x plus 2 power x minus 1. And that's what I'm doing here. Right? 2 into 2 power x, because we are doing 2 power x plus 2 power x minus 1, right? So it's 2 into 2 power x minus 1. You guys are clear with this, right? So, and all I'm doing now is just creating the tree array, right? Like it's just, and I'm putting 0 into. So usually whatever value that you put here, right? The default value that you put here, usually that should be a value that is considered as a no-op for what tree that you're building, right? So because we are building a sum tree here, right? Since we are building a sum tree here, what is a no-op value for a sum?
Yeah, 0.
0, right? So that is why it's 0. And that's why I've noted down in my comment saying that, 0 is any dummy value, because for summation, 0 is the dummy value, right? But if we are building a max tree, then we would actually initialize it with minus infinity, because because in a max tree, you cannot actually put 0 over there, right? Because, you will actually jeopardize your the maximum value if you have negative elements. Right, like so 0 is not a right value for max tree, right? So for max tree, the right value to initialize there would be minus infinity, right? But for the sum tree, it's just 0. Yeah.
For min tree, it will be opposite.
Yes, exactly.
Max, yeah, okay, makes sense.
It'll be infinity.
Yeah.
Yes.
Yeah, makes sense.
Right. So you guys get this also, right? Like, so far, all we have looked at this, like these 4 lines where I'm getting the input array, storing it in my own array, whatever it is, right? And then I find out what the length is, I store it in the n variable. Then I figure out what the tree size is. And it's nothing but it's not even related to segment trees. If you have a complete tree with the total number of elements as, which is the number of leaves as, like some particular x, then what is the size of the tree? And that is a formula that I'm using here. It's 2 into 2 power x minus 1. And we are done with this, right? So we get the tree size, we create the tree array, we are done. So now I start the recursive process, right? I think if we understand this recursive process, everything else is like really like, because all the update and everything kind of follows a similar, right? So what I have to do, right? Like, so in order to build this tree, right, I recursively build. So even though I build it from here, the way we showed was we start at the leaves and we build it, right? But when I use recursion, we always go from top down, right, rather than bottom up, right? So all I'm saying is, hey, the crec, right, which is actually my my recursive function to build this to create this segment tree, it takes 3 values, right? One is, what is the starting range for this node I? What is the ending range for this node I? Right? So I have to give it 3 values, which is the start, end, and I. And we can actually look at this picture to see what those values are, right? If I'm going to start at my root, right? So because it's a complete tree, given that I have n elements, then the starting value for the root, the starting index value for the root is what? 0, right? Because the root represents all the elements from 0 to n minus 1, right? So the starting index that root represents is 0. The ending index that root represents is n minus 1, right? And root's actual index value is 0, right? It's simply based on, you guys see the 0 and 0,7, right? Those are the 3 values that I want in order to build my segment tree here. The start, end, and I, right? So the start is, what is the starting range that I represent? End is, what is it? I think I should probably even, you guys get that, right? So it's nothing, it's nothing but the start range, comma, end range, comma, curve tree index, right? So those are the 3 things that I actually take as an input, all right? And once I have this, so and when I start with, for example, right, like, so I want to build, so what is the segment tree that I want to build? I want it for starting range of 0, and then because it's an 8 element array, so it's basically len of whatever this n, right? So len of this array arr minus 1, right? So that is this. And then when I start the segment tree, which is the root's tree index is always 0, right? And that's exactly what I'm passing to the first call here. CREC of 0, and the because 0 is the starting index of the range, n minus 1 is the ending index of the range, because I want to represent all the elements in the n element array that was given to me, right? And then that 0, the third thing that I'm right, that's actually your tree index, right? And because when I call the CREC function, I'm calling it to build the root, right? Like, so because root will automatically call to build all the recursive levels, right? But initially I just have to call to build the root, and that is why I'm passing 0 over here. Right now, what does root does, right? Let's forget the base case for now. Let's look at the else case, right? So when I come over here, and then when I want to build this root, right, you guys realize I can't actually build this root until I build my left subtree and right subtree. You guys agree to that, right?
Yeah.
Right, so I have to build my left subtree first, and then I have to build my right subtree first next. And once I have those, right, then my left subtree will give me the value 10, right subtree will give me the value 26, and then I can simply put what the value for my root is, right, which is actually 36, right? So the very first thing I do is you guys remember, like, when I have when I represent 0, 7, what will my left in a complete tree, right? Like, what will my left represent? My left will always represent, like, if I find the mid, my left is going to represent between 0 to mid, and then my right is going to represent between mid plus 1 to the end, right? So start comma mid, and then mid plus 1 comma end, right? So those are my ranges for the left subtree and the right subtree. And what is the actual tree index for the left subtree? That's basically 2 into I plus 1. And then what is the tree index for the right subtree? 2 into I plus 2. So when I call my recursive function, I simply use the values that I just discussed over here. All right, I simply say, like, this single line, so this mid line basically calculates what get mid, a simple function that simply says the start plus n minus st by 2, because I think we are going to use it in multiple places. I didn't want to write it everywhere, right? So you just get using your start index and end index, figure out what your mid value is, right? And then all you do is your value, right, which is basically this value, your value is this 36, right? It's nothing but get the value for your left, get the value for your right, and add them. And that's exactly what I'm doing here, right? CREC for get the whatever this parameters for the left and whatever the parameters for the right. So what are the parameters for the left? So as I said, right, for your left subtree, you know that you found mid, right? So your left is basically starting from your start index to the mid is what your left subtree is going to represent, and your right subtree is going to represent the remaining, right, which is mid plus 1 to end. And then your actual tree index, you guys saw that, right? In a complete tree, if your index is I, your left is 2 into I plus 1, your right is 2 into I plus 2, you simply pass to the CREC function what those indexes are, and then you're basically done. So, and then finally, once you do this, you simply return your, because as you have to return what your value is, right? Because you have to return it to your parent, so that your parent can actually fix the values for itself, and then it will return the values parent, right? Because when you go from the top down, it actually gets constructed from the bottom up, right? Like, so you go all the way to the leaves, and then from the leaves, you basically push the values up to the parent, and then the parent will figure out what his value is, and then he'll push his value to his parent. His parent will get his value from left and right, and then he'll update his value. He'll push his value to his parent until he reaches the root, right? And if you guys think about it, right, the base case becomes extremely simple, right? The base case is all about, whenever I reach the leaf, right, which means I cannot split anymore. See, until that particular point, right, if my total number of elements is greater than 1, I can always split it, right? The ranges can be split, but my leaf is the level where each node represents a single value, right? And single value means, as I said, if you guys see here the brackets, it's always 0, 0, 1, 1, right? The starting index is that index of that particular value, and the ending is also the same index, right? Because it's just a single value, and that's all my base cases, right? If start is equal to end, right? Like, if your range is nothing but the same, right, then that is your leaf, right? In that case, you don't split anymore, right? Like, that is where you stop the splitting and simply store whatever the value at that particular index is, right? Like, so from your original array, right? Like, so you simply store that into your tree index, whatever the tree index that was passed to it. You guys get that, right?
Yes.
The base case,
It's clear. Yeah.
right? Like, so it's simply, you know, like you start from the root, which represents your entire array, and then you split it into half, give the left and the right, right? So you have two halves now. You go all the way. When you finally reach that leaf, you don't have anything to split anymore, right? So you simply store what are in your index, right? In your tree index, which you got by I. So one thing that we have to understand why we are passing all the start, end, and I, right? Because this, when you look at the self.tree, right, you actually, I mean, just looking at the tree alone, you generally, like, looking at any one particular node there, you actually don't know these values, right? These values always have to propagate from the root, right? Because you only know that the root covers this particular range to this particular range, and the root is at index 0. From there on, it is actually easy to, like, as you propagate forward, you can always figure out what your left is, what your right is, and what the tree index for your left is, and what your tree index for the right is, right? So, like, you have the 0 to mid, mid plus 1 to end. Sorry, not 0 to mid, start to mid, mid plus end, mid plus 1 to end, to figure out what your left and right ranges are. And your left index is nothing but 2 into current index plus 1, and right index is 2 into current index plus 2. Right? So anything that you guys think that you want to discuss on the construction of this segment tree?
I'm good with it. I'm good with construction.
Right, like it's kind of straightforward, right? And if you guys look at it, once we look at this, if we practice, not even practice, if we just look at this for 2-3 days, I think it will be, it's almost like a you know, like a simple tree construction, right? Like, so you get it, and then, you know, like, you find the mid, pass it to the left, pass it to the right, you know what the base case is, and then you're basically done. The only small complicated, not complicated, but a little bit more involved thing is, you know, what is the tree size, right? So, and that's based on the property, the property of a segment tree. And there is one line that I've included over here, right, which is basically in the get tree size, the first line. All I'm doing there is, if my actual n, the n that is actually the size of the given array, let's say it's actually not a power of 2, right? So, but it is easier to think of a segment tree as a complete tree. So all I do is I convert it into a power of 2. That's all I'm doing. That seal of log of n is nothing but, you know, like, I just take the log of n, and then when I put the seal to that, right? So that would be like, you know, like the next power of 2 that contains all the n elements, right? And then I use that particular x value to actually figure out what the tree size is. That's all it is. It's pretty it's a straightforward. That line is there to handle array cases. Because you can't always expect your arrays to be powers, I mean, in the length of your array to be power of 2, right? So you have to add that line to just make sure that you're actually okay with the, you're always constructing a complete binary tree. That's all it is.
Yeah, so this CREC function will be same except the summation here on line 17, right? If we have to construct min, like range minimum, range maximum, all we need to do is change line 17 to have min and max, right?
That's it. That's all it is. Yeah. Perfect.
Yeah.
Perfect. In fact, like if you want to write a generic one, right, what we can do is, instead of doing this a plus b that I'm doing in that line 17, I can simply say some function of a comma b, right? And then that function, you can either pass a sum to it, or you can, I mean, based on the problem, you can define what that function is.
Yeah.
Right. Like, so, yeah, what you're saying is perfect. You know, like the point where we kind of, you know, like, given whatever I'm getting from my left side, whatever I'm getting from my right side, for the summation thing, you're actually adding it. For the min thing, you'll probably do a min over there. For the max thing, you'll probably do the max over there. That's all it is. Yeah.
Even if we take the perfect tree as a size, it should still be okay, right? As long as you are maintaining the limits of your.
Which one?
Like in this case, you told that we have to take the tree as a complete tree, and this is the logic for that to do it.
Yeah, this x is right. So, I mean, because, yeah, if you're, all I'm trying to do is, like, you know, like, I'm given some n. For example, in this case, let's say n is 6, right? So when I do a log to the base of 6, right? Log to the base 2 of 6, right? So what I'll actually get is some 2 point something, right? So, and then I actually take a seal of that, which will actually be 3, right? So, which means I'm just taking the next power of 2 that actually contains this total. So in this case, if the given input array element size is 6, I'll basically consider that, you know, like, take it as 8, which is actually 2.3.
Okay. Yeah.
Right, but I think so what you're kind of saying is like we don't, what you're saying is we don't have to do that particular step. That's what you're saying. What you're saying is like, like I can simply construct this whole tree just exactly based on the elements that are given to me, and only and only create this the only place where where the total size of the tree is used, if you guys look at it, right, is the place where I construct that self.tree equal to 0 into whatever get tree size, right, at line 22, right? So as you said, right, there is a almost very similar approach where like they construct the segment tree without actually making it a full complete tree, right? Like they actually construct it looking at the way they handle. Yeah, you have to have a little bit of index handling here and there for that. So here, when you do this way, right, like you don't have to like do any extra check on the indexes and kind of thing. You're guaranteed to always hit the right indexes at every single point of time without any checks. And I thought this version was easier to remember and easier to kind of reason about than the other versions where you don't actually have to create that extra space for the tree. The logic will still remain the same, right? Like even what they do is exactly the same, right? Like they'll take it, they'll divide it, and then they'll give the mid to this guy, they'll give mid plus 1 to n to that guy, like and then they'll propagate it all the way to the leaf. So all those things are same, but at least I mean, like I didn't get a chance to look at how that algorithm worked today, but whatever I could think of, the reason why I chose this approach is where you kind of assume that you're given an input array is complete, and if it's a power of 2, if it is not, you at least create the tree assuming that your input is a power of 2. It makes life a lot easier when we code it. That's all it is. So any questions that you guys have with respect to the construction of this? Straightforward, right? Like, so it's exactly as we described, right? So when I call this, I'm going to call using 0,7, right? Or 0, whatever my length of input array is, right? And then I'm going to give the root index as 0, right? And simply do the recursion, figure out the mid, call it on the left, use the index plus 1 here, 2 into index plus 1 and 2 into index plus 2. And then like at the base case, if it's a leaf, I simply store, like I go, because at the leaf, that's what we do, right? Like, so at the leaf, whatever whatever the index that I'm getting at the leaf, right? So this particular index that I'm getting at the leaf is nothing but the tree index. In this case, the 7, right? So that's the actual tree index, right? So because when in this whole construction algorithm, at every node point, you are given what tree index you're operating on, right? So the tree index for this, but the first one element, the tree index will come as 7, and then your start and end will come as 0, 0, right? And all you do is like you go to your original array, grab whatever is at the start or end, both are the same, right? So you grab whatever is at index 0, and then you take it and put it in the tree index, which would have been 7 as it is passed to you, and you're done. And that's all you're doing here. Right. So now, if you guys are clear with this, right, now actually let's see how a query can be answered, right? So the query answering is also like really, really simple. Let's say, for example, right? So the query that usually in a segment tree that we have, it's always a range query, right? Given a particular range, give me whatever that function is. So in this case, the function is sum. So give me the sum of all the values between a range. Very first simple question. If I tell you guys saying, okay, given the input array is 1 to 8, right? And then I tell you, hey, give me the query range for the sum for indexes between 0 and 7. What would you guys do?
Root.
Exactly, right? So your 0 and 7 perfectly fits with the root, right? So then I don't have to look at any other node, right? Like I simply can go look at the root, and if I can somehow figure out that that's all that I need, right? I simply return that value and then I'm done, right? So question 1, very simple case, we have handled it, right? Let's look at another question, right? So let's look at what if I actually ask the interval to be, I think if we deal with this one, so let's say if I give you the interval as 2,6, right? If I give the interval as 2,6, right? What would be the procedure to get the values by touching the minimum number of nodes? Let me explain you the procedure, right? So 2,6 comes, right? Yeah.
Before going to that 2,6,
Yeah.
so if query is 0,7, we know it is a root, it is 0th index, right? But how do you determine 0,7 if the input is 0,7? How do you determine it is level 0, or I mean to say it is 0th index itself?
Right. So perfect thing.
The
Right?
input is 0,7, right? But you need to know, okay, 0,7 is nothing but 0th index.
Exactly. So how do we determine it is, you remember like in the build function, for example, right? Like when we start from the root, right, we actually tell the root, right? Like, so because the root doesn't explicitly store what ranges it covers or what its tree indexes, right? So we kind of tell the root, like what is the current tree index, and we also tell the root what is its start and end value it covers, right? Because it's because for root it's known, right? Like if let's say for example, I'm because whenever an update, whenever a query comes in, right, I'm always going to pass the query to the root of the tree, right? So and the root of the tree, when I say okay, fine, query, and then I want to pass the start index and end index of the root, and then the tree index for the root, those three values are known to me, right, for the root.
Correct.
Right, like so when I pass itself, you guys actually look at, so I didn't want to go into the code because like I just wanted to deal with the logic, right? So first, but when we look at the code, we'll see that, you know, when I call this on the root, I'll actually tell the root saying, hey, you know what, you cover indexes from 0 to 7 and your actual tree index is 0.
Yeah.
Right, so that is what, so that 0 basically represents the root, right? So I'll tell you what, you know, like, okay, this is the index that we are looking at right now, right? Because we don't actually have the concept of a node here, right? So I have to, like, I need to know what index right now I am in, right? So so when I call it on the root, I basically call it on 0 because I know 0 is always root, right? And I also know the range of the root always, right? Because it's a complete tree, I know for sure that root covers all the values between 0 and 7.
Okay, got it. Yeah.
Okay. So I kind of tell it, I kind of tell it to the root, and when the root even calls it on its subchild, right? You guys even saw, even in building, right? When it calls on its left and right, it'll exactly tell to the left node what its range is and what its tree index is.
Yeah. That makes sense. Yeah, it perfectly makes sense.
So those values are always passed on as part of the recursive functions to all the subchilds. And the root, we already know exactly what it is, and to the child, it'll always be passed on by its parent. Those three values, right? So in this diagram, those three values of, you know, like because the actual tree only stores your the 10, 26, 36, 3, 7, 11, 15, and 1, 2, 3, 4, 5, 6, 7, right? So the actual tree only stores those values. So where are then to form this tree, where are we getting the other things that we need, right? Like what is the actual root, what is the actual tree index of it, and what is the actual left and right ranges that it covers, right? The start and end ranges that it covers. So we know from the root, so we pass it to the root. The root, whenever it calls it, it's because all the queries, updates, or even building, right? They're always going to come from the root and travel downwards, right? And to the root, we pass exactly what it covers, and the root will pass it to its children, and then they will pass it to their children and stuff.
Yeah, got it.
Right, cool. So now that it's 0, so yeah, assuming that, you know, in that particular node, we know that, you know, hey, I am 0 and I cover ranges 0,7, and let's say the query is also 0,7, right? Like it comes to the root basically checks that, okay, hey, you know what, I satisfy the query, the root will simply return its value, done, right? Now let's look at this one other interval, which is 2,6, right? Because if we successfully look at 2,6, we are basically done with the query part, right? So if we look at 2,6, right? So the very first thing that I see is, you know what, is that 2,6, right, is my current node that I'm looking at, whatever that node is, right? Is that node completely contained within the query or not? That is one check that I do. If it is, then I actually return that particular value. That is why when 0,7 came, the reason why we didn't even recurse or do anything, right, is because I got a query range that is either equal to me or greater than me, right? That is when I simply return. right? We'll see why that works that way, right? We'll actually, I mean, if you look at this whole example, we'll see why. But just stay with me, guys, for a couple of minutes, right? So the first check that I do is like, does the query interval it completely contains what my current node's interval is, right? So then I simply return. I don't have to, because if it completely contains it, right, which means it needs the full value of me, right? So the only reason, okay, I think we have to understand one thing, right? The only reason why I would have to even look at traverse my query into my children is because like I cover a much larger range, right? And which means that I cannot perfectly answer whatever query that is coming to me. Then I'll I'll percolate it to my children, and my children will be able to figure out the exact combination that covers the correct range, right? Like together, right? But if whatever range that I am in, right, if it completely is contained within the query, right, so in that case I can simply return my value, right? Because if I pass to my children, what do my children have? My children just have the sub values of me, right? So the children will not give me any more information than what I can give, because I myself is contained in the query, right? So I simply return what my value is, right? So for 2,6, for example, right, 2,6 is not actually contained in the current node. You guys agree to that?
Sorry, one question here, Johnny.
Yeah.
So here you have 0, 7, right?
Yes.
Is there a scenario where you will get -1 and 8? You're saying this will be self-contained in it, like
right?
The query.
So
I'm asking, for
exactly.
example, -1 and 8. Can you please show that scenario?
Yeah. So we will. So the thing is, you will never get that scenario for the root level, but you will get that scenario for the other levels.
How?
We'll see. So if we take the same 2,6 example, we'll actually see how that is possible.
Okay, sure.
Right? Like the question that you ask is like perfectly valid, because like when because like why would be, but at the root level, if you think about it, right, like I mean my total number of elements, it's only 0 to 7, right? Like so I'll never have you will never give an index that is less than 0 or greater than 7.
Correct.
Right? So at the root level, it's not possible, but the way the algorithm works, you like in the next 30 seconds, you'll actually see how it goes, right? So as I said, if the current node range gets completely contained within a query, like you mentioned, -1, 8, then I simply return myself, right? There is no need to percolate it to my, right? So that's, but in this case, is that the case? That's not the case, right? Here, I actually see that whatever the range that I'm getting, 2,6, it has an overlap with this particular node, right? Which means when it has an overlap, right? Which means I can't answer it. Right? It's overlap, but it's not a complete overlap, right? It's not a complete containment, which means I can't answer it, but my children will be able to answer it. That's the meaning of the overlap, right? There is also a third case. You have 3 cases always, right? Case 1 is my interval is completely contained in the query interval. And for 2,6, that's not the case. Case 2 is my interval is completely outside the query interval. Right. So and that is also not in 2,6 case. So for like the example that he gave, -1, 8, there could also be, let's say I give you an interval -1, sorry, let's take I give you an interval 8, 12. Right. So if at the root level 8, 12 comes, right, there is no, I mean, as a root you only cover 0, 7. There is no way your children are going to cover anything that is outside of this range, right? Because your children are just going to be subsets of what you cover, right?
Correct.
Correct. So if at the root level, for some reason, if I get a query saying 8, 12, I will not even percolate it to my children. I'll simply return 0, because, hey, you know what? Whatever query that you asked is not even something that I cover, which means it's not something that any of my children is going to cover, which means I can simply return 0 and then I can move on, right? So that is another case that we have to, when we look at the code, that's one more case that we'll write. There are only 3 cases, right? Either completely contained, in which case I can return myself, right? So because whatever my children can answer, I mean, I actually have the total thing, and you completely cover me, right? The query is even bigger than me, which means I am part of the query, so I return myself as well, right? And that's the case -1, 8 you mentioned. And the other one is like 8, 12, where, you know what, I don't even cover what you're asking for, just return 0 over here, right? The third is what 2,6 satisfies, right? The third one is, like I am not completely contained, and I am also not completely outside, which means there is an overlap between me and the query, right? And if you guys draw 0,7 and 2,6, you guys can realize that, right? So there is an overlap there, in which case I don't know how to answer it, right? So I don't know how to answer it, but I'll allow my children to answer it, right? So when there is an overlap, what I will do is I'll simply pass on the query to my children. So how do I pass on the query to my children? To my left child, I will basically calculate what the range of left child is, right? Exactly how when I created, how did I figure out what the range of my left child is? It's always you find the mid, and then you know that it's 0, mid is a left child. So I calculate the same thing, right? That I calculated when I constructed this. So when I call it on the left side, I give because when I called on the root from the outside, I gave 0, 7 and 0 as inputs, right? Now to the left side, I'll give 0, 3, 1 as input. To the right side, I'll give 4, 7, 2 as input, right? Because those are the tree properties, right? I have to pass to the left child for the left child to understand who it is and what it covers, right? And it can only come from the parent. That's how we build this tree, right? So I give those necessary values, and I also tell the left child that the query interval is 2,6. Right? Because that's the query interval, right? The query interval is not going to change. It's always going to be 2,6, right? And I also tell my right child that the query interval is 2,6. Okay, so you guys got that, right?
Mm-hmm.
So now what will my left child do? The left child knows that it covers 0, 3, and then it knows that its tree index is 1. So in this case, we don't actually use the tree index to compare the values, right? But we still need the index, because when we call on my left and right, how do I figure out what the value for the left and right is, right? It's 2 into index plus 1. So, but the left child looks at 2,6, right? And it sees whether 0, 3 is completely contained within 2,6. Is it the case? No, right?
No.
Because
Yeah.
because yes, 0, 3 is actually your 0, 3, like your 0, 3 has an overlap with 2,6, right? But your 0, 3 is not within 2,6, right? If it was minus 1,6, then it would have been completely contained, right? But it's 2,6, right? So there's an overlap. So it meets the overlap criteria, right? On the left hand side. Let's only look at the left hand side for now. Let's finish the whole left hand side, then we can go to the right hand side. Right? So what the left one does, you know what? I am not completely outside, right? Because there is an overlap, right? So if it was outside, then maybe if the query was for 4,8 or minus 5 to minus 1, then I know that I'm outside, right? But here it's not. There is an overlap. So what he will do is he will call his own, exactly what the parent did, right? He will figure out what the range of his left child is, which is 0, 1, right? So, and then he'll figure out what the tree index of the left child is. It is 2 into my index, which is 2 into 1 plus 1, which is actually 3. He'll figure this, and he'll pass the same 2,6, right? Because I want 2,6, right? So he'll pass 2,6 to his left child, right? And he'll also pass 2,6 to his left child, right? Now we are actually looking at nodes 3 and 4 in the diagram, right? We're looking at nodes 3 and 4 in the diagram. And now you guys have to tell me what's going to happen, right? Let's look at node 3, and the input query interval is 2,6. Which
left
case
will
does
return
it?
0.
Perfect, right? Because
Right
0,
will return 0.
yeah, exactly. So left is going to return 0 because 0, 1 is completely outside the 2,6 query interval, right?
Yeah, okay, I got it now. Yeah, here the left one is completely out, but the right one is included in the range. So
exactly. And now if you guys look at
2,6.
the exactly,
Correct.
now if you look at the right side completely is contained within the interval 2,6. My query interval is bigger, 2,6, right? My right side is only covering 2,3, right? But it is completely contained within the query interval, which means your right side will actually return the value 4. Sorry, not the value 4, the value 7.
Yeah, I was thinking that he will split and send it, but you're propagating the query range to the leaves, right? So
yes.
Yeah,
exactly. So logically also, right? I want 2,6, right? And this right child is having 2,3, right? So he actually contains everything his subtree contains.
Correct.
Right. So and this 2,3 is definitely within within the query interval 2,6, right? Which means I have to include that in my result.
Yes.
Right. That's all it is, right? So 2,3 will return the value 7, right? And but 0, 1 as that actually satisfies another case, right? That we have not seen so far. It's completely outside, right? There's no point in again giving original, right? Like so 0, 1 will terminate the recursion there and return 0. 2, 3 also will terminate the recursion there and return the value 7, which is stored in it. Perfect, right? So you guys saw how we started at the root and we started at 2, 6, right? We went all the way and we went until the nodes, right? Where it is either completely outside, no point in going further, or it is completely inside, in which I completely cover whatever I can cover. Again, no point in going further, right? In that case, I return the whatever value that I have, right? So that's actually the summation of indexes between 2 and 3, right? I return it. And then the left guy returns 0, and it actually comes to the parent. Like in this particular case, what the parent will do, the parent will simply because it's the sum query, right? So in the sum query, the parent will always like get the left sum and then the right sum, and then he'll just return it to his parent, right? So far, the third node returns 0, fourth node returns 7, and they both return it to the node 1, right? That is marked 1, and he basically will just add those two values, which is 0 plus 7, and he will return 7 to his parent, which is actually the root node. So root node, by executing this on his left tree, he actually got the value 7. Now you guys have to tell me what happens on the right subtree, right? Because when you have an overlap, you always execute both on the right tree and the left tree, right? So we figured out what happens on the left tree. Now on the right tree, what's going to happen is I again on the right tree, I figure out what the right tree's range is using the mid value, and then I send what the start range is, what the end range is, what the tree index. And this is going to be constant for every query, the create function, the update function, or whatever function, right? So it's just a way the segment tree is represented and how we kind of move forward with it. Right? But it is also going to send the range. It's also going to send the range 2, 6, right? And 4, 7 is the range for the right node, which is basically we are looking at the node 2 now, right? So now, which case does this fall into? 2, 6 and 4, 7.
It will propagate to both childs.
Perfect, right? So there is an overlap case, so it propagates to both the child. So now let's look at the left child first, right? So left child is 4, 5, and I am actually looking at 2, 6.
Completely covered.
Perfect, right? So the query is wider than me, right? And in which case I will not propagate further, so I'll return 5 over here. Sorry, not 5. I'll return the value 11.
Yeah.
Right, the 5 is the index value, but I'll return the actual my value, right? I'll return 11 over here, right? So far, if you guys note down, I've written 7 so far, right? That is that from the node 4 return 7, and now I'm returning 11 over here. So it's 7 plus 11 so far. That's all I've written, right? And it will not propagate to the side. Now let's look at what happens on the right side, right? On the right side, you actually have 6, 7, right? So and on the input range that I want is 2, 6.
Overlap.
There is an overlap, right? So here, because all ranges are inclusive, right? So which means like there is an overlap 6, and I can't decide it, right? So what I will do at this particular point is I'll again
recurse on both childs.
Recurse on both sides, right? So now I'm looking at node 13 and node 14, right? Like, and I would have passed, the 6, 6 as start and end indexes. I'll also pass the value 13, which is the tree index based on, like my mid and the usual formulas, right? I'll also pass 2, 6. Now let's look at the left side. So 2, 6 is the range, and my left side's range is 6, 6. So which case does it fall into?
Complete overlap.
Complete overlap, right? So that guy is actually going to return his value, which is actually 7. All right? You get it?
Yeah.
And then on the right hand side, which is 2, 6. So what is that case? That is 7, 7, and what you're getting is 2, 6. That's completely out, right? That's completely outside, right? So that's going to return 0. So far we have seen that there is one return value 7 and one return value 11 and another return value 7.
Yeah.
Right? All these will get propagated to the top, to the top, to the top. It will finally come to the root. When the root sums it and sends it, it's going to give the values 7 plus 11 plus 7, which is
25,
right? Now, if you guys actually manually sum the values between the range 2 to 6, 3 plus 4 plus 5 plus 6 plus 7.
25, yeah.
That's it.
7 plus 3, 4 plus 6, yeah.
Right, like 7 plus 6 is 13, 13 plus 5 is 18, 18 plus 4 is 22, 22 plus 3 is 25. Right? So you guys can see what is happening, right? Like logically, if you guys look at it, it's also easy to visualize it, right? You get this range 2, 6, right? So you percolate it to the root until you reach nodes that can satisfy one range of it completely. And in this particular case, the way it got split was, it got split into 2, 3. That was one range that covered completely. It also got split into, what is the 11, right? So that is 4, 5, right? 11 was 4, 5. It also got split into 6, 6. Those are the three ranges that returned you the values, right?
Mhm.
The ones that returned the value 7 plus 11 plus 7, if you guys look at the range of those, 7 that returned was range 2, 3, 11
2, 3.
returned 4, 5, and then the final 7 that was returned was 6, 6. Now you guys look at the actual ranges, right? 2, 3, 4, 5, 6, 6. That's actually 2, 6, right?
Mhm.
Perfect. That's all it is, right? So we got 2, 6,
Yeah.
and we just split it, and then we percolated to the children. We stopped either when we are being completely covered or when we are completely outside, and then we move, right? So all we are trying to do is, like, we go up to that node, right? Like that we know for sure we can get that value in there, right? Why and how can I get the value in there? When I know that, like everything under my leaf has to be included.
Yeah.
Right, which means like I am a sub range, right? I'm a sub range within the big range, which means I don't have to pass this to my leaf because I already have all the values for the leaf, right? And I know for sure that all my leaves have to be included. That is why we do the check, right? Am I completely contained within this query? That's what the check we do. What does it mean? It actually means that everything in my leaf is actually part of the query. That is the meaning of am I completely contained in the query, right?
Mhm.
And
So updation from here is very simple, right? Like know the previous value, remove that one till the parent path, like the root path, and add the new value to the root, to the child to root path.
Right. So the way we have constructed, yes, what you're saying is like what you're saying is basically bottom up, right?
Correct.
Right. But if you remember in this particular segmentary approach, right? Like we always start from the root. Right?
I see.
You see that, right? The way we percolate is, whether it's an update query or whether it's a build query or whether it is a range query, right? We always start from the root and then we percolate it downwards, right? And the way that is actually going to look. So two things, right? So do you guys first want to look at the code for the range for the query before going to the update, or shall we skip the code?
Yeah, we can take a quick look at the code.
A quick look at the code, because the code is exactly going to do what I mentioned. It's not going to do a single thing outside, right? So this is the code here, which is the sum range, right? Where I want to get the sum of the range. And if you guys look at it, this line 48 is where I'm actually passing it to the root, right? And to the root, I'm telling what the start index of the root is. It's always 0, and the end index of the root is always self.n-1, right? And then what is the root's tree index? It's always 0, right? And then what is my I comma j? The I comma j is basically the actual range for which I want to find, which is coming from the function itself. Right? And then this is the recursive function I do, right? And in the recursive function, all I do is check the three cases that we discussed so far, right? The first case, right, is am I completely, right? Is the current interval completely contained in the given query interval? That's all I'm doing in the first one, right? So if my QST, right, like if my start is less than this intervals, this current node's start, and if my end is less than this, if my end is actually less than the query's end, right? So which means I am somewhere in between this query, right? The query started before me and the query ended after me, right? In which case, and that's the first line, that's the line at line 44. Right? So that's case one. Next is the case two, right? So where I see whether, the query ended even before me or the query starts even after me, I ended, right? That's the second one where I'm completely out. I return 0 there. Right? And the third one, right? Okay, which means I'm an overlap. And what do? I have to pass it to my children. What do? I find the mid, and then I actually that's line 46. And then finally I do a recursion on my children. And when I do the children, I always pass in what the left index is, which is basically the start, which is my start, right? The left is always the start. The right for the children will always be mid, right? So because we are going to split on the mid. And then the actual left index, the tree index for the child is always 2 into I plus 1. We do the same calculation for the right. And then we pass the complete query start and query into the child also. So 2, 6 is passed to the child also. And that's it. You guys said that.
Okay, so the minimum case will be the same. Put a minimum or maximum here on line 47.
Exactly, that's it. That's it, right? So wherever you're doing that plus right here, right? So, like wherever you're doing a plus on any operation you're doing on the value, there you will substitute it with whatever function that you need.
Correct. Okay, yeah, got it.
That's all it is, right? So this function is clear for you guys, right? So can we go to the update one now, right?
Yeah.
Okay, so in the update one, right? The update one is also like, as you said, I think the logic that Arvind mentioned was like, why don't we, okay, we're going to update this value. So, propagate it all the way to the root, right? Which is actually perfect. But the way we constructed the segment tree, right, is we always start from the root because we know the ranges for the root and then we propagate from there, right? If we actually had a tree structure with the parent pointers, we would do the way Arvind mentioned over here. But because we don't have that and we have this array thing, the way I'm going to do it
here
is like,
we have the parent pointers, right? Parent is nothing but I minus 1 by 2 or something.
Oh yeah, we can, yeah, exactly, yeah, we can actually do the yeah, right. So the access to the parent pointers is there. So if I'm going to update a specific value, right, so then I just have to traverse all the way back to the parent. Yeah, I think we can do that. Yes, you're right.
Yeah, I was thinking something like union find, where we do a find, we propagate till the parent is itself.
Oh, we start, yeah, in the union find you always start with the with whatever value that you want to join, right? Which and then you go all the way to the parent, and then okay, yeah, I think you can do it that way also. You can actually start if you want to, let's say in this case, for example, if I want to update index 8 to something, right? So I update the index 8 and then I find out what the difference in the update value, right? Because that is what I want to add to all the nodes, right? So for example, not index 8. So in this case, it's 0 to 7. Let's say all I want to do is like replace 8 with the value 9.
Correct. So we have to add 1 in the path from
exactly. So exactly, right?
Yeah.
We have to do is like in that entire path from 8 to the root, we simply have to do an add one. So
but,
we can.
But how do you? Sorry, go ahead.
No, I think that's a valid approach, right? The recursion that I had in mind for this approach, or even what the code is doing, right? I start from the same way I do for the query and the build, right? I actually, I pass that index, right? So for example, in this case, the index that needs to be updated is actually the value to be updated from 8 is 8 to 9, which means the index that I want to update is 7, right? I mean, the example that we saw was update the index 7 from 8 to 9. That's the right example we saw, right?
Correct.
Right? Update the index 7 from the value 8 to the value 9, right? So when I pass this to the root function, I know what the difference is, right? Because I want to update 8 to 9. So I will figure out what the difference is. So I calculate the difference as 1, right? So and then I pass to the root saying, hey, you know what? The value that has to be that the diff that needs to be added to the entire path is actually 1. And then I'll also tell what is the actual index that needs to be updated. I need those two values, right? I need the update diff and I need the update index. So for this particular example, the update diff is 1, the update index is 7. You guys agree to that, right?
Mm-hmm.
Yeah. So now let's say I pass it to the root, right? So how do we percolate it, right? So the root basically figures out whether the update index 7 is something that it actually covers or not. And it actually covers it, right? So 7 is contained within 0,7, right?
Yes.
So when it contains it, all I'll do is like I'll update my value by just doing a plus of diff, right? I'll just update my 36 to 37, and then I'll pass it into my left, and then I pass it into my right. I'll just propagate it, right? Now on the left hand side, the update index is the same, right? Because I'm just updating that index 7, right? So update index will be 7, and the diff is also so for all the calls, the update index is going to be 7, and then the update diff value is update diff is going to be 1, right? But on the left hand side, I see that my range 0,3 does not even contain the index 7, right?
Yeah, true. So, right? You will drop the recursion from there.
That's it. That's it. I simply end the recursion. I don't do anything from there. So left hand side is done. On the right hand side, because 7 was passed to it, and I know that my interval is 4,7. I know that 7 is contained within me. So I'll update my value from 26 to 27. I'll just add the diff to it, right? And then I'll send it to my left hand side. And then on my left, it is basically 4,5, and it sees whether 7 is contained within or not. It is not contained within it, so I cut the recursion there. But on my right hand side, 6,7, right? So I know that I can't, I mean, I actually have that 7, which means I also have to update my diff, right? So I just do a 6 plus 1, which is, sorry, 15 plus 1, which is 16. And then I send it to my left and right? So on my left, right, so which is actually the covers index 6,6, right? And it sees whether index 6,6 contains index 7. Obviously not, so it will just stop the recursion over there. And then what 7,7 will do, 7,7 will see whether it contains it. It obviously contains it, so it will basically update over there. And there you cannot again split it, right? So because you are at the leaf, so when you are at the leaf, you always simply return after updating yourself from 8 to 9. That's it.
Yeah.
Right? And if you guys look at the code, it's exactly the same, whatever we just discussed, right? So for the update one, like I calculate, so look at line 36, I figure out what the diff is, right? So I want to update, like this particular index with this value. I go and look at the old value, which is self.array of I. I find the difference, right? And I first actually update. So this update function, whatever we are doing, whatever we saw so far, it's only updating the tree, right? So we also have to do the actual update on the array that I have stored, right? So that is why I have that line 37. That's the actual update on the array itself. And I also find the difference in line 36. And then I call the recursive function on the root. As always, the start of the root is 0, the end range of the root is n minus 1, and the root's recursion index is 0. And then I for the update, I need to give it 2 values, right? One is the actual index that is updated and the actual diff value, this I comma diff, right? And they are not going to change, right? And then if you look at
sorry, what is this 0 here? The third one? The third 0, which you're taking in 38.
So if you look at line 48, right, the first 3 values, and then if you look at line 38, the first 3 values, right? And
okay, is it the position?
Exactly, that's the tree. And if you look at line 23, the first 3 values, it's always it's the tree index. Exactly. Yeah, that is what actually defines what that node is, right? It's the tree's index.
Mm-hmm.
Right. Like, so that's basically.
But how are you using this one? Okay, so yeah, you are using on line 34 and 35 to call to the children. Yeah, got it.
Oh yeah, exactly. Right? Because they have to know, you will always figure out what the range is based on what your start and end is, right?
Mm-hmm.
But yes. what your actual tree index is, it is something that your parent will tell you, because your parent knows its tree index, and then it knows that the left is 2 into I plus 1 and the right is 2 into I plus 2. So that's the tree index. So as I said, right, like, so for all these calls, right, all these recursive calls, every node, right, in order to form the full node in a tree structure, it needs a few things, right? One is the actual value that is there, right? So if you look at here, there are 4 different things that actually form each node. If you guys realize, right? Every node is formed by 4 values, right? One is, let's look at the root, for example, right? One is the value 36. That's the actual value contained in the array. Right? That is 1, right? But what are the other 3 values that this thing represents, right? Or that is associated with this particular 36, right? What is the range it covers, which is actually a 0, n minus 1, which is for the root, right? And also, what is the actual tree index? Yeah. The tree index can also be considered like a node name for it, right? So
yeah. Actually, it is not level. Actually, it's a node name. Actually, kind of.
Actually, this will not scale with the minimum and maximum case if you do like this, because you're getting what I'm saying. So can you go back to the code one?
The code, yeah.
Yeah. So here we are calculating the diff and we are propagating the diff, right? But in the case of minimum, if you calculate the min of root comma the current minimum, or what I'm trying to say is, like, we can't
apply. Okay, let's think about it, right? So so what you're saying is the case for the update is what you're saying there might be an issue.
Yeah, actually I'm trying to use the same code for the maximum, minimum, and sum.
Right.
So
cool. Let's see, right? So let's look at what happens when a particular value changes, right? So let's say a particular value changes from 6, 8, right? So in this case, for example, what changed was 8 got changed to 7, is it?
9.
Sorry, 8 got changed to 8 got changed to 9. So and I know that a particular index is is changing. So when it comes to me, can I figure out, I mean, I know that, I mean, I can always figure out that the index is contained inside me, right?
Yeah.
Oh, so
So
what
the
is the problem? Yeah, exactly, right? So I know that the
No,
index is contained
actually,
inside me. My min is nothing but whatever. I mean, I will update my min if the current value that I'm actually updating is going to be the new min or not. That's all, right?
no. I think he has
I
a
think
point.
no, because
Yeah,
you get min from the left and you are updating in the right tree.
but
So
it'll.
No, no,
Go
root
go
will
ahead.
no,
have
no,
the
no.
minimum from left tree.
Which one? Sorry.
Okay, so can you
Let's.
go to the tree? I can show
Okay.
you.
Okay. Sure. So and
So
let's take. Yeah. Yeah.
Maybe
suppose
you do this instead of 8 to 9, do 8 to 6.
yeah,
So
8 to 9 also works fine. I can
for,
show you the problem. So
okay. Sure.
Okay,
you
yeah.
have 1 here, right?
Yep.
So you get 1 in the root as minimum.
I get 1 in the root as a minimum. Yes.
You get 9 here now
Yes.
at the place of 8.
Yes.
So you are planning to find, sorry, 9. This will be changed to 9.
Yes. 8 should be
And
changed to
you will,
9. Yes.
okay, what you did previously was to check the minimum of these two things.
Get the
Minimum of 8 and 9. Previously you were subtracting 9 from 8.
right. So for the sum we are doing the diff, right? So but here we like here for the min one, I don't need the diff, right? For the min one, I just need to know what the index is, and instead of the update diff, I just need to know what the update value is. I'll simply keep the value as it is and pass it on. So here the update value is what? The update value is 9, right?
So you will keep checking it from the root till the bottom to
Yes,
that
right.
point.
Yeah, exactly, right. So let's look at how the call is going to look, right? For the call at the root, the call is going to come. It's going to give me 0,7,0. That's always fixed, right? So that's the parameters for the root, and then it's going to give me two things, right? One is it's going to give me what is the update indexes, and update index is what? It's the same one that we did for the sum also, right? The update index is 7, right?
Mm-hmm.
And what is
Yes.
the update value?
9.
9, right? Cool. So now that I have 7 and then I have 9, right? Now, how do I change this? Instead of adding, right? Like all I have to do is I just need to see whether that update index 7 is contained in my current interval or not. Here, is it contained? Yes, right? At the root, it's contained, right?
Mm-hmm.
Right? So now all I have to see is the minimum, and for this particular minimum thing, the root would have had a value of 1, right?
Yes.
Right? Now all the root has to see is like, hey, you know what? So far my minimum is 1, but because of this change, there is a new value that is actually coming into picture, right? Should my minimum value change or not? That is all it is, right? So how does it going to do? It's simply going to see whether, like, is it going to be the min of whatever it has stored, which is 1, comma, whatever the new guy who's coming in, right? The new guy who's coming in is actually 9. It's going to take the min of 1, comma 9. It's going to be the same, which is actually 1.
Yeah.
Right, and the same thing, if you percolate it, right, let's even look at one more level, right? So let's look at on the right hand side, right? So on the right hand side, because that is what 7 contains, right? So until now on the right hand side, what will actually be the value that is stored? Instead of 26, because it's a mint tree, it would probably have stored 5 there, right?
Yes.
Right, at node 2, correct, it would have stored 5 over there, right? So when the actual update value comes to it, right, so what it's going to do, it's going to check whether this new value that is going to come into my subtree, will it change the minimum in my subtree or not? That is all it is going to check, right? And in this case, obviously it's not going to change, so it's not going to update its value, but it's going to give it to its children, and the children will do the same, right? It's just trying to see whether this new value is going to displace the minimum. If it is going to displace the minimum, it will update the minimum, otherwise it won't.
Yeah, correct. Yeah.
Right, so that's all it is.
Yeah, my bad. Actually, I was thinking something else.
Okay. Instead of the sum, we are simply, as I said, right, like, so in the sum we have to pass the diff, but here we won't pass the diff, we'll simply pass the actual value, and all I have to check is, what, because I am considering this guy because, like, this guy is in one of my subtree, right? So in which case, if this guy comes into my subtree and he's lesser than the minimum that I've stored in mine, then I know for sure that I have to update my minimum, right? Because that is the new minimum of my subtree, right? If it is not, I won't do it.
Yeah.
Or we can also do like how you construct, right? So you keep going until the end, you do whatever update. When you keep coming up, it will return some value. You will just like whatever you did in the creation. Like if it's a function, you're going to call that function. It's going to decide what it has to do.
So yeah, so what you're proposing is like, you know
That's the
what?
bottom-up approach.
Yeah, exactly.
Bottom-up
That's
approach.
exactly. So that's what
So,
Aaron's going to do, right? You basically
yeah.
change from the bottom, and then you basically apply the function at each of your parent to make sure that you have updated your parent as well. Yes.
Yeah, exactly like how we did the creation of the tree.
Yes. Yes.
Right.
Yeah.
But this is also perfectly works. Yeah, correct. You're right.
Right. So
I was also thinking of to pause the difference, but based on the need and problem, you would change what you would
value
pass
that you
for the
pass.
update function. Yeah.
Exactly. And if you guys actually look at the code, right? So I think we are looking at the code for the update thing, right? So the line 38, the first three parameters are always going to be the same for the root, right? So it's basically the start of the root, the end of the root, and the actual tree index for the root, right? And then your I and diff, right? Your I is actually your update update index, and then your diff is actually your update diff, right? I think I've named them correctly at line 29 in the recursive function, right? The last two parameters are your actual update I and then your update diff, right? And again, you do the same thing here, right? If you figure out that this update I, right, it's not even inside your interval, that whatever you represent, you simply return. You don't have to do anything, right? You don't have to go to your children, or you don't even have to update a difference. But if that is not the case, then you know for sure that, you know, like it's contained in an interval. So you for the sum case at line 31, you're simply doing this. So whatever the value that you store, you're actually adding the diff, right? Like you're simply adding the diff. And then, yeah, so the another base case that you have to take care of is like, because even in the base case, you first have to update if you're contained, and then you see whether, you know, am I the leaf or not. If I'm the leaf, then I don't actually recurse. If I'm not the leaf, I find the mid, I do the exact same recursion on my left and right, and then that's it.
Oh, you have done it before, right?
Which one?
So on line 37, you have already handled the case of like the start equal to end for the current position, like the updated index. That's why you are returning from there. The line 32.
Yeah, line 32 is line 32 is I've reached the leaf, right? Which means I cannot recurse anymore. There is I don't have any children left, right?
Correct. Yeah, like I'm asking when both are equal, you didn't. You have to check for one case, which is the line 37.
Oh, line 30. So that line 37 is just doing something completely different. Line 37 is updating the actual array, not the tree.
I'm
you see
still
that, right?
concerned with the tree. Like, how is tree updated then?
Yeah. So with the tree is over here, right? So so we have two data structures now, right? One is the actual tree.
Correct. I'm looking at how tree is updated.
Yeah. So how the tree is updated is, so even at the leaf, line 31 would have actually updated it.
Okay. Yeah.
Right. So that is why you see that, right? So 31 would have, even if it is a leaf, 31 would have updated the leaf. What you thought that I think you thought 37 was doing 31, right?
Correct. Yeah.
So, but 37 is doing something different. 37 is actually updating the original array that you have.
Yeah. Correct.
And then the leaf is updated at 31, and then your 32 is, okay, I have updated it. Now, before I recurse on my left and right? So I just see whether, you know, like, am I a leaf? And then I basically bail out if I'm a leaf. That's all. Otherwise, the call to the recursion is almost the same, right? Like your first three values are always the same. It's always start to mid, and then for the next one, it's always mid plus 1 to end. And then your indexes are always 2 into I plus 1 and 2 into I plus 2. And the last two values are what your update I and update diff is, and they are never going to change for the entire recursive routine.
Yeah.
That's good, right?
Yeah.
That's all, folks. Actually, the entire segment tree, right? Like, so it's very I found this, like I think I mean, I didn't remember today when we got this problem, right? But like Madan said, so it looks like I've taken a session on this, right? So that is when I kind of wanted to find like one way which is very easy to reason about, right, and very easy to build, and we don't have to remember anything in this code here, right? Like, we just, if you know the logic, it's very easy to construct this whole segment tree, you know, like without remembering the code, but at least remembering what the structure should be.
Yeah. So I'm good with this, but what's the difference between segment tree and binary index tree?
Let's not even go into that for now, right? So the thing is, like binary index tree solves a subset of what segment trees can solve, right? Like, so there are a couple of and it uses a completely different approach than segment trees. It does that. If you guys remember, there is always a square root approach or something, right? So where you know, instead of building it logarithmically, like from a complete tree and then moving forward to the root, right now, to be honest, I've looked at the logic of bit. I've understood it at one point, but right now I don't even know what the logic is. But only thing
No,
that I can tell is,
is it okay if we learn segment tree and leave the binary index tree
yes,
aside?
it's okay to learn segment tree and leave binary index tree. It is not okay to learn binary index tree and leave segment tree, because segment tree covers so let's say if segment tree covers some set of problems, right? Your binary index tree will not be able to cover anything other than a subset of your segment tree problems, and it is not even like an intersection. There is no intersection at all. Your bit, anything that you can solve using bit, you can actually apply segment tree and you can solve it. Literally no quantities over there. But there are a lot of problems that you can cover only using segment tree that your binary index tree cannot cover.
Okay.
So which means that, so your binary index tree is completely contained within your segment tree. So if you know segment tree and if you know this, you don't even have to really spend any time on binary index tree.
Okay, so is it straightforward that when an interviewer asks, we can go with this approach?
Yeah, I guess so, right? Like, so to be honest, right, the only problem with binary indexing, if you look at the code for binary indexing, it is actually even more easier than what I mean, to be honest, I mean, if you look at this code, right, I don't think this code is complex, right? Like it's very straightforward, right? Like, so we understand what the parameters are, we know how to recurse, and we know how to handle the base case. We are basically done with this, right? But binary index tree, if you guys look at it, the reason people use it in competitive programming is it's very simple, very easy to code. But at least like when I probably more than a year back, when I read about it and tried to understand how the binary index tree logic works, right? Your segment tree logic is very straightforward. You know exactly what you're doing at each level. Very easy to explain to the interviewer also how we are building the segment tree and everything, right? Your bit takes a little bit more effort to make the interviewer understand what you're doing and why you're doing.
Okay.
So I mean, again, if you're curious and interested, definitely please go ahead and look at binary index tree and how they are implemented. It's a super useful algorithm to learn. It's but from an interview point of view and from problem point of view, if you want to learn one thing out of these two, it's probably going to be segment tree, because this will cover a bigger set of problems than your bit.
Yeah, got it.
Not that I have anything against the binary index tree, right? So
yeah.
So the time complexity will be O of height of the tree.
Always log n, yes, exactly. And in this case, right, because we are considering
log n or log h?
H is equal to log n.
Number.
H is equal to log n. So it's big O of h, which is equal to big O of log n.
So say that one more time, please.
So your height, right? So your height will be actually log n, right?
Height will be log n, correct?
Yeah. Right. So it's basically the order of height. So normally you consider say it is order of log n.
Okay.
Right. The update is order of log n. The sum range is order of log n. The actual construction is n log n, I guess, right? So because because I mean you are obviously touching
more than n, yeah. And constructing the
it's probably, so let's actually look at it, right? Maybe it's only big of n because it's probably big of 2n, right? So because at each point I'm calling it on it's actually just big of 2n. Yeah, exactly. It's just big of 2n, which is actually
yeah, correct.
Yeah, it's not n log n, sorry. It's big of 2n, which is big of n.
Actually, it's big of 4n.
So the loops run for you're touching 2n, and then how is the 4n coming into picture? So what am I missing there?
So if you take your number as 5, your number of nodes as 5, then you look for 8.
Oh yeah. So so that n that I mean, right? It's actually I agree. So that n is you always have to convert the n to some power of 2, and it's
Nearest
bigger.
power of 2.
Yes.
Actually, we are not doing, because he's stopping at when start equal to end, right? The start and end, he passes the original array's length. So he will not actually go to 6, 7, 8. Although array has a size of 6, 7, 8, I don't think he will. The
We won't
construction will
actually.
go,
Okay.
because you always return when the both of the, and you're passing the values from 0 to n minus 1. N minus 1 is the array length of n minus 1, not the multiplied that 1, right? 2 into n power minus 1, 2 power n minus 1.
I agree. Yeah, I think I think what Madan says also is correct, right? In the sense that we may not go all the way back to the
Extra spaces.
the dummy ones, the dummy nodes that we have. We may not go. So we have to look into it a little bit. But I think you're right. We may not go. But yeah, it's safer to say it's big of n.
Yeah.
Right. So usually it's just big of n, where n equal to some 2 power x, or in this case, in this case, it's just big of n.
Yeah.
Right. So because we have to draw the tree to see. I know for sure it will touch because if my node as a parent contains one node that is contained and one node that is not contained, right? One node that's a dummy. So we'll touch at least one of those dummy nodes, right? But and your dummy nodes are always at the leaf, right? So your dummy nodes are always at the leaf. So the question is, will I touch all the nodes at the leaf level, even though they're dummy, right? So so that is the actual question. So when I come to the root and then I would I think I might simply pass on to there, and then at the dummy level I might actually check whether I'm out of bounds or something. But usually we don't do that, right? So we
Can you go to your code, Johnny? Yeah. If you see at the line 13, if you see you say when your start is equal to end, you would just put this back and then you would return.
I agree. So we will touch some dummy nodes, but not all the dummy nodes.
+1 actually. It will be just +1.
Maybe that one thing where that it actually is. Yeah, maybe you're actually
right. Even for query, you would whenever it overlaps, you don't worry whether what overlaps. You just pass on to both of them. Yeah. They decide whether it falls under me or other person.
Right. Cool, guys. So I think I hope this was okay for you guys, right?
Yeah, it's very useful actually.
It's perfect. It's like it's amazing.
It's just one implementation that I always found to be like repeatable. I mean, we can always remember this thing. That's what I usually think. But
yeah.
If you guys, there is one more version which doesn't convert it into a complete tree, right? Like, so that whatever that I'm trying to do here, right, the get tree size, right? So I'm not actually, so it doesn't convert it. If you guys look at the code for it, there are a few extra checks and stuff like that has to happen for that particular version. You guys might want to do that, but at least from an interview sake, I don't think when we solve a problem using segment tree, the interviewer will still continue and tell us that, hey, why are you using that extra space? I'm optimistic that will not be the case, right? I mean, if we are writing code, I mean, I know segment tree is not that hard, but still most people don't use segment trees, right? So for this particular problem, if we are using segment trees and then we're doing, right, that that creating that extra space over there, I think it's probably going to be the least of the things that the interviewer will be worried about.
Yeah, but when he comes to the space exactly and he's interested, suppose if we have tree of like the number of nodes are number of elements in array is 33,
Yep.
then he might be pissed off because we'll create exactly double and which is more.
Again, yeah,
Like
that's
it
the
grows
thing,
with
right?
n, right? So
There is a trade-off for this particular approach, right? So this particular approach, it's easy to, at least like, I mean, as I said, like right now I haven't looked at the other approach where they use the exact memory, right? Like, so I haven't looked at it, but there was a reason why a year back I chose this approach and tried to stick with it, mainly because this is something that at least I thought for me, it was easy to remember and easy to reproduce in an interview.
yeah, it will
Right,
be
so
difficult at 40. If I reach 40, I will forget.
right. It's
Yeah,
not.
this is good.
It's also about so the like you're solving the problem, right? And there's a little bit of extra space that you create, right? So maybe we can actually if you guys find some other segmentary code that kind of, because the logic is the same, whatever I explained, right? It's going to be almost the same. That there will be some extra handling to to make sure that we don't touch those spaces. Probably just index checks might be. I mean, maybe it's actually easy.
It's like yesterday we saw this edit distance contest question, right, where you use 2D array, but it's also possible to do it in 1D. So it's like a improvement where we can think of, but I think solving with 2D is.
I don't even use arrays for edit distance along LCS. I simply use DP and recursion.
So that is completely different, Madan, because there you are reducing it by n-fold, right? It's not like reducing space in n. Now we are trying to reduce from 2n to something less than that, but there it's completely like from n square to n. So it might matter. We should go for the n one.
I see. Okay. Yeah. It makes sense. Yeah. I will not deny it. Yeah. I mean, there it's like when you start, you think like 2D and then, or I don't know if you, I don't know what you guys recommend. Do you directly go to 1D whenever the problem comes, or like Johnny said, he generally goes with DP and memo on DFS?
Yeah, I simply do recursion because it's more easier for me to think and write. So,
if there is a problem which I already solved, I'll go for the same approach. Otherwise, I try to do DFS with memoization.
Yeah.
Okay. And here sorry, go ahead.
No, that's right.
So I was thinking. So here, when we don't have, in this approach, we are not worried about like this edge case, the index out of bound, all those edge cases criteria, right? That is really a key during that time pressured interview time.
Right. I feel so when you have a 45-minute interview and then when you're given a problem like this and then you code a segment tree, right? Like so. The expectation would be that you're able to reason about the segment tree, you're able to reason about the approach. Why? I mean, are you able to explain to the interviewer why whatever the data structure that we code actually works that way, right? Like so, as long as that is there, and then you're actually able to give a nice, elegant code to solve this problem, right? So I think like you're 99.9% in, and the net of creating that extra space probably won't even come into the discussion, but maybe if it comes, we can always I mean, once I write this code, right? Like obviously, I hope that I won't have time to write it, but I don't think it's going to be like a lot of work to convert this into creating the size for that. It's just that some index stuff has to be a little bit more carefully written. Yeah, so that's as you said, Madan. So here, I don't have to worry about any index check until I reach the base case, right? If ST equal to and I reach the base case, I stop the recursion, right? So there, like
Yeah.
when I go into my left and right, I might actually go into areas where my ST might be greater than end, or maybe whatever the ST, one of those indexes might actually be out of bounds with the actual length of the array, kind of a thing, right? So in that case, I might actually have to have something to just check. Otherwise, I think my personal opinion, knowing this is good enough. But if you guys are worried about that extra space, then I would definitely ask you guys to have a look at the other one. The logic would still be the same, whatever we did, right? But the code will a little bit differ.
Yeah, but do you think that these are the template kind of codes and we should be able to write this in 5 to 10 minutes?
I think so. So
because union find is kind of similar thing where
exactly, right? Like, so and even let's even look at a try, for example, right? So let's say you have never coded a try before, never.
Correct. It takes a lot of time to write.
And an interview, yeah, exactly. And an interview to code a try, it's actually not a trivial task.
Correct.
Right, like most probably, even doesn't matter how smart and brilliant someone is, right? Most probably in that 30 minutes, they may not be able to, they just for the first, they have maybe heard about the try, but let's say they have never coded about it, but they heard about it. They know how a try works in a very generic approach, but they never coded. Now suddenly go and ask them to code, right? I don't think it's that super intuitive to code about, right? Like, so.
Correct.
Yeah. So what you're saying is like true. Like the only reason people don't go for segment trees is because there's a general perception that segment trees are hard, because if you guys look at it, right, so most segment tree problems come in the hard range. So there are no medium problems in the segment tree range, right? Like, so and a lot of implementations are not like as simple as we saw over here, right, to reason about and stuff. And people also look at binary index tree. And binary indices are extremely hard to understand unless you go through the rigorous procedure of finding out how they are constructed and stuff like that. Long story short, if we know that segment tree problems are becoming a common day-to-day happening, I think it's better to remember this template and keep it in our fingertips, so that tomorrow when a problem comes, right? So I don't have to worry about it. It's a very, 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 very staple ask from Google, segment tree questions, especially this range sum mutable, range sum immutable. I don't think Google asks a range sum mutable anymore, or even the range sum immutable, right? Probably they'll ask something along the ranges of that. There's one more thing called range sum query 2D mutable or something. So Google has advanced to that stage now.
Okay, by the time I give Google interview, they will move to 3D.
See, that is the thing, right? Because I heard this very recently from my friend at FBA, right? Like he heard from his director saying that the actual conversion rate of on-sites to offers is really high ever after this COVID started. And if you guys look at it, it's actually true, right? Look at our Telegram group, the big group.
Mm-hmm.
How many E5 offers did we see? We saw 4 or 5 offers in the last 3 months.
Yeah.
Right, like, so because everyone is preparing their asses off, and then like it's like you go and some candidate comes and then you tell him, hey, what, check whether this binary search tree is a valid binary search tree or not. That guy will laugh at you. I mean, the candidate will internally laugh at you, right? Like, so he won't obviously laugh in the interview, but internally his mind will be laughing, right? Oh shit, man, why this simple? Okay, perfect, I can nail this down. And then like he'll simply probably he'll write the solution in 2 to 3 minutes and then he'll move on, right? So which means
there is sorry, just a joke. There is a movie. Tamil, it's a father and daughter thing. But to join the daughter to the LKG or the UKG in India, right? He has to do a lot of study in the for the convent. I mean, parents will go to class. The headmaster he'll ask, please ask me something. Please ask me something. Some question. You don't know to ask any questions. It's like that. What you're saying.
That's the thing, right? So And you know what? The one thing that I really don't. So my friend who went and joined Facebook, right? So it seems like he went. They have these internal forums where they talk about, right? Like so, they have very specific channels and stuff to talk about interviews and stuff, right? So it seems he went and not only him, a lot of people have posted. It seems recently that like, hey, everyone knows all the problems and all the stuff and stuff. And it seems like these guys went and posted saying, you know what? Let's actually create a new set of questions and not give the same questions again and again. I was like really pissed off because this guy got in because he prepared from that standard set, right? And now he went and he's going to go there and change the whole thing. Right? Like so, it's really amazing. But anyhow, it's fine. But yeah, but again, yeah. So we have
Somebody
to.
is able to prepare all these 400 questions thoroughly, right? It cannot be just a mug up, right? It has to be practice and at least months of effort to get in there, get to that level.
Yeah, I think that's their idea behind, right? Like, so why they don't change it is because they think is like, if you can do this, right? If you can put this much amount of effort, then you can come here and also do the work.
Yeah.
That's
Yeah.
so they are basically yeah, like that's what they are kind of like, because Google, that's the opposite, right? Google doesn't care what you know, right? Because they make sure to ask you something where where they twist it off and then like see whether you can think it out or not, right? Like so Google doesn't test your memory, right? So even though you still need memory, but that they basically see. That is why I think attending these contests and all these things, because you see a question for the first time, right? Like and it might follow a similar pattern, right? Like so you still might be able to leverage what you've seen before. But in my honest opinion, right, let's say let's take the lead code contest that went by, right? You guys look at that breadth first search question. There was that, I think second or third question was a BFS question, right? The island wall and thing.
I couldn't attend, sorry. Yeah, but I watched your conversation.
Right. Like, so there was this one question, which is that island or wall or whatever, right? I don't know whether it's a binary search thing or whether it's a lead code thing. One of those two things. There is a question where it was just the BFS, right? Like so.
It's a BSIO, binary search actually.
Exactly, right. So that question is still a new question, right? So that's not an old question. I don't think we have seen that question before, but it resonates so well with one of the set patterns, right? So it's very easy to reason about, mainly because we have solved some similar BFS questions, and it's very easy to figure out the pattern. But on the same thing, you guys look at the ad hoc question, right? Like so the one where there is no set pattern to it, right? Like so and there is no way to to like you haven't seen the question before and there's no set pattern to it, right? Now and how do you actually come up with a solution? That's the question, right?
Perfect.
Right. Like so that I think that is what requires a lot of like constantly, the first time you do it, probably it doesn't come, right? Because there's no pattern. I can't, let's say, I start from the beginning of the array, start from the end of the array. If there is some kind of pattern that I can apply, then, all my previous experience is going to help. But what if there is no pattern to it? Right. So that is what they call as ad hoc problems, right? Like, what if there is no pattern to it, right? So that is where, all are not just seeing the previous patterns, but our experience of seeing problems that we have not solved before, and then thinking hard about it, and then trying to solve it by ourselves, right? Either in the contest or even when we started doing LeetCode initially, maybe like 2-3 years before, right? So at that time, when we look at even an easy problem, right, it was hard because we have not seen many patterns. Maybe this pattern was a common pattern, but maybe I have not seen before, or maybe it's an ad hoc problem that doesn't have a pattern, and I have not seen enough. Enough problems to kind of somehow figure out that, oh, you know what, I can do this, I can do that, or whatever, right? So okay, the only reason I brought it is because that's where Facebook and Google differs.
Yeah.
Right. Like, so for Facebook, they look at your effort, right? And they reward your effort, saying, you know what, if you have put this effort, you can come here and you can do what we want you to do. Right. So Google has this different notion saying, Okay, you do whatever effort you put, right? Like, so you solve 2000 LeetCode problems, I don't care, but I'm going to twist it and see whether you can actually like think it or not. And that is why I think because any given problem, right, for like on some day we'll be able to solve, on some day we'll not be able to solve, right, a new problem, right? There is no guarantee. So that is why I think Google is always people go and join Google for even lesser money than Facebook, right? I've seen people take a pay cut to go and join Google, right? And Google lowballs you like hell, right? You're basically you're selling. I mean, it's like you're basically selling. Uh, 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 you're selling your actual phone. Google will pay you the price of a dummy phone. Right? That's how they do it, right? Like unless you give them counter offers, like hey, you know what, I got an offer on FB. Even then, they don't give you the level, right? They always down level you.
Mm-hmm.
Right, like so, I think I have only heard one L5, one or two max in the last 2 years. Some post in blind, and some post in LeetCode Discuss, I guess, where a couple of people talking about L5 offers as a positive sign. Nowhere else I've seen a Google L5 offer in the last 2 years in any forum anywhere. Right. So, but in Facebook, even in our small, like 400 people Telegram group, there are like five E5 offers in the last 3-4 months.
Yeah.
Which means that we have a real shot at Facebook. Right. It's purely preparation. And it's all LeetCode, guys. Like, I mean, as far as I understand, I know at least one person pretty I mean, I basically talked to him the day before interview, so I know how he does system design and stuff. He got an E5 offer, and his system design skills are like almost close to like less than medium level, right? But he had prepared a LeetCode like hell, and even after the interview, he told me that like his LeetCode, all his LeetCode rounds went extremely well, and he actually said, I did system design so bad, they're either going to reject me or they're going to ask me to come because I did LeetCode so good coding rounds. They're going to, and I think he also did behavioral well. So he said, I'm going to get another system design round, or it's going to be a reject. Hopefully they consider my LeetCode 4, but he actually got an offer straight away. No second system design. Right? So I think what we are doing in the evening carries much larger weight than system design.
Yeah.
And I don't know what level that you guys would aim for. So, but for E5, the offer is really, I think for E4, it's like 100K less, but for E5, right? My friend's first year salary for E5 is a little more than $500,000.
I have only 1 year experience in the past and 6 months here, so I'll be aiming for SD2 next June.
Yeah. So you'll be aiming for E4 or E3?
I don't know the exact ranges.
Okay,
E4,
sure.
I guess. So yeah, SD2 equivalent in Amazon.
Oh, it's probably E4, right? So, if you're aiming for E4, for example, right, you're literally looking at somewhere around your first year salary. I'm not talking about your total comp, but your first year salary will get close to 400K, including that joining bonus. Like my friend's annual salary is like, I think it's 400K, and his joining bonus was 100K. And they have refreshers, right? Every year, in addition, top of that, I think his first year salary is even more than $500,000, because the first year itself, they give a refresher. The refresher, I think, is actually, the refresher is 160K for 4 years.
Oh.
So every year you get a 40K refresher on top. We are talking about real money, guys, here.
Yeah.
Yeah.
Right. Like, so what we earn outside in 10 years in Facebook, you can earn it in 2 years and move on. And
it is okay to I have good experience, but it is okay to go and try for any of the